Hello, in this lab we're going to do dynamic braking on a three-phase motor. So this is the circuit we're going to be using. I'll supply a copy on Learning Hub so that you can follow along and print it out beforehand. So we've got our three-phase supply. We're using a neutral for the control, and also to supply our bridge rectifier. We're going to supply the bridge rectifier with 120 volts AC, which will give us approximately 108 volts DC on the output. We've got two contactors. We've got M that starts the motor, and we've got DB that's going to do the dynamic braking, and we've got one timer relay with one time contact and two instantaneous contacts. The two DB contacts here supply DC to two lines of the stator when we want to brake the motor. We've got M and DB are interlocked through this normally closed DB contact, where as soon as we start the braking, this is going to open and prevent M from restarting if the start button is pressed. We've got a one stop button, but we're using a normally closed contact to stop M, but we're using the normally open contact to initiate the braking. So if we didn't press it all the way down, we just pressed it enough to open this, this is going to brake before it's going to make. So we could coast to stop if we wanted to. If we wanted a coast stop button, we could just put a stop button here in the circuit. Sometimes motors that you want to brake, maybe you only want to brake it at certain times. Sometimes you want to just let it coast to a stop. Dynamically braking a motor, we have to supply it with a lot of current to get enough torque to stop the motor in a reasonable amount of time. So it tends to heat the stator up quite a bit if we repeatedly braked it. Okay, so when we hit the start button, this is closed. So we'll have power flow, we'll energize M, M seals in, and the motor starts. So when the motor is running, when we hit the stop button, this is going to brake before that makes. So we're going to de-energize M, and we're going to close these 2 points. And when that happens, TR is closed at this point, and we energize both TR and DB. Now at that point, TR is going to start timing. Now the time we set would be the approximate time we expect it would take the motor to stop. So we don't want that set too long, because then we're going to apply DC to that motor stator for too long and it might get too hot. And so that will start timing. DB will energize. So that's going to close this contact, and that supplies AC power to my bridge rectifier. The other side of the bridge rectifier, the AC side is connected to the neutral. So at that point I'll have 108 volts of DC across the DC terminals. So you can see this terminal goes straight to T1, and this terminal goes through. We had to put some resistance in the circuit because the windings, the way they're connected, it's a delta run motor. We're getting about 1.5 ohms. And we're connecting to two lines. So that's going to be the sum of the resistance of this parallel series circuit. And that's 1.5 ohms. We're supplying about 39 volts to the stator between these 2 points, about 39. Remember, we have 108, so the cone heater has to drop the rest of the voltage. We could probably put a little bit more current through it for a short period of time, but we have limitations of our supply circuit. Okay, so when DB energizes, we supply AC to the AC side of the bridge rectifier. We get DC out. These two close, and we're applying about 39 volts DC, and that's giving us about 18 amps through that circuit. When the timer times out, TR opens and TR and DB drop out. So TR is what's holding this circuit in, and that drops out and the braking stops. Okay, so now we will connect the motor up and see what happens. Okay, we have our circuit wired up. We've got our dynamic braking contactor here. We've got our motor starter contactor M here. We've got our start-stop station. We've got our pneumatic on-delay timer. And we've got our bridge rectifier over here. Again, we're limited to about 20 amps of DC to this circuit. So I'm going to start the motor. And we'll zoom in on the shaft. This motor does not have any load on it, but we can see the effectiveness of the dynamic braking. So now I'm going to hit stop. So that stopped it pretty quick. I could probably set the time down a little bit, but that's fine. About 18 amps brings it to a complete stop. Okay, so now we're going to wire up or connect the flywheel load, and we're going to find it is going to take a lot longer to stop, but it's not going to take as long to stop than if we didn't have a brake. Okay, now we're going to start it with the high inertia flywheel load. So that took about 23 seconds. Took about 23 seconds to stop. If we had let that coast, I think we tested it earlier, it takes about 4 minutes to stop. So we went from 4 minutes without a brake to 23 seconds. And you know, that can be fairly critical if you have to service a machine and that machine would put the process down. So you can save many minutes over many days. It doesn't take long to pay for the installation of a dynamic brake.